So now we're continuing on with the previous problem, and we're moving to part B that wants us to show first that g prime of 2 equals g prime of 5, and then we're going to use this result to show why there is a value k in the interval such that g double prime of k equals 0. So anytime we see a derivative or a second derivative trying to be equal to 0, we should think Rolle's theorem. I mean, you can also think mean value theorem, but Rolle's theorem is specifically equal to 0. So there's three hypotheses to Rolle's theorem. The first is to show that the endpoints are equal, and that's actually what they want us to show here, right? So this is really step 3, right, of using Rolle's theorem. So g prime of x is f prime of f of x times f prime of x. So g prime of 2 is f prime of f of 2 times f prime of 2, which is f prime of 5 times f prime of 2. And then g prime of 5 is f prime of f of 5 times f prime of 5, which is f prime of 2 times f prime of 5. So using both the commutative property and transitive property, we can see here that g prime of 2 equals g prime of 5. So now we've got the third hypothesis to Rolle's theorem. Let's go back to the first two. So the first one is that it must be continuous. And how can we show that? So we know g is a composition of differentiable functions. So g is differentiable. And since it's differentiable, that implies that g is continuous on that closed interval 2, 5, and g is differentiable on the open interval 2, 5. So there's our three hypotheses for Rolle's theorem. It's continuous on the closed interval, it's differentiable on the open interval, and our endpoints are equal. So by Rolle's theorem, there exists a k value within that open interval 2, 5 such that the instantaneous rate of change of the derivative, which is the second derivative, at that value equals 0. So notice we use the first, the second, and the third hypothesis to use Rolle's theorem to prove our statement.